Welcome to NPTEL online course on fractal and multifractal. In the last lectures, we have discussed about fractals and their history and how the fractal objects are different from the Euclidean object. Now, let us try to construct the fractal systematically. So, for that we need some preliminaries. In this lecture, we are going to discuss foundations which we need to know for constructing the fractal in a metric space. Usually, the fractal has two way of self-similar properties. One is approximate self-similarity and exact self-similarity. As we mentioned in the last lectures, if fractal has exact self-similarity, it is known as regular fractal or deterministic fractal. So, here we are going to see the fundamentals of constructing fractals, in particularly deterministic fractal in a metric space. Let us see the foundations. Though upcoming lectures we are going to discuss the following foundations: the metric space and complete metric space, contraction mapping and fixed points and Banach contraction principle. So, after covering all this subject, we will go for the construction of fractal in a metric space by using all these foundations. So, let us start with the metric space. So, what is metric space? A metric space is a non-empty set X together with the function D from the Cartesian product of X to the non-negative real numbers 0 to infinities. So, X is a non-empty set and D is a mapping from X cross X to closed interval 0 to open infinity, that means non-negative real numbers. This distance we are calling as a metric or distance if this D must satisfying the following property. The first one, distance between two elements x and y. If you are taking x, if you are taking 2 points x and y in x, the distance between x and y must be equal to 0 whenever both the points are same points. So, this can alternatively defined as follows: as distance between x and y is strictly greater than 0 whenever, that means if and only if x and y are distinct points. So, this we can write in alternative way, and distance between x and y equals distance between y and x for every pair of element in the set x. So, finding the distance from one point to other point and other point to this point will give the same value, and the distance between x and y, x and z less than or equal to distance between x and y plus distance between y and z. That means, if you are taking intermediate point y, then finding the distance between x and y and z, the sum is greater than the distance between x and z. So, this can be summarized as follows: the non-negative real number D of x y, D is a function, this is called the non-negative real number, measures the distance between x and y in the space x. Distance is 0 if and only if two objects lies on the same position. If you are finding the distance between 2 points, if both are lies in the same position, then the distance equal to 0. Second point, distance is symmetry with respect to the position of the object. It means the distance between 2 points is same whichever the point it is measured. If you measured one point to other and other point to the first one, then you will get the same value. The distance between 2 points x and y cannot exceed the sum of the distances from x to the intermediate point z and from y to z. So, the distance cannot be exceed whenever if there is a intermediate points appears in between 2 points. Then if D is satisfying all these 3 property, then we can call it as a metric or distance. A set together with the metric, we can call it as a metric space. Let us discuss some examples of the metric space. Consider the real number system R. Then the function d of xy is defined as follows. That means modulus of x minus y, where this modulus is defined as modulus of x equals x whenever x is the positive numbers, x equal minus x whenever x is a negative number, x equals 0 whenever x is 0. So, here the modulus is defined on the real number system. So, if you are taking any pair of x and y in r power 2 and r cross r, the Cartesian product r cross r, then distance is defined as x minus y. That means d of xy is defined as x minus y. This distance we usually called as the usual metric or standard metric on real number system. Let us try to prove this distance function modulus of x satisfying the metric properties. Let us discuss one by one. First property, we need to verify this x is a function from r cross r to close to 0 open infinity. So, you can see the range. If x is positive, then this will give the positive value. If x is negative, then it will get the minus of x. So, again it will be a positive number. If x equal to 0, it will give the value 0. So, the range of this modular function is 0 to infinity. Hence, d of x y is greater than or equal to 0 for all x comma y belongs to R. Now, the first property of the metric space, if modulus of x minus y equal to 0, when these terms will get 0? Only when both the points are equal. So, first property is satisfied. Now, we will move on the second one. Check the modulus of x minus y can be written as modulus of minus x minus y. So, this can be also written as modulus of 1 times modulus of x minus y. So, modulus of minus 1 we will get the value 1. So, modulus of x minus y we obtained modulus of y minus x, and we need to prove the third property, that is called the triangle property. So, observe that the modulus of x is always greater than the plus or minus x, greater than or equal to the plus or minus x for any x, not y, maybe for all the x, modulus of x greater than or equal to plus or minus x. By this inequality, modulus of x minus y, now I am adding the intermediate point x minus z plus z. I am adding this minus z and plus z, that adding this z with this term, then minus y. Then this can be written as, by this property we can write modulus of x minus z plus modulus of z minus y. So, we arrived at the triangle property. So, this function modulus satisfying all these three property, therefore, we can call this function modulus is a metric on R. So, therefore, R with this modulus function we can call it as a metric space. This metric space we are calling as a Euclidean metric space or usual metric space. Sometimes we can call it the standard metric space. In the same real number system R, now let us try to define different metrics. So, here let X be a non-empty set. So, we can take R or any non-empty set. Define the function d of x y equals 0 whenever both the points are equal. 1 whenever the points are distinct points. So, this is a d is a function from x cross x2. More specifically, the range is 0 and 1 only, because it is only giving the 0 and 1. So, this is a subset of closed 0 and open infinity positive real number. So, the range satisfying the metric range, and this one can verify this function d satisfying all the three properties of the metric. This function together with any set, or instead of r, instead of the x we can use the real number system, then r comma d we can call as a discrete metric space. Though this is true for any set, as we already defined one metric in the real number system, this metric discrete metric also forms R as a metric space. So, this is one more example for the metric in R. Now, let us see some other example of the metric space. If we choose x as r power n, so r power n means set of order n tuples. That means we can take x1, x2 up to xn, which is the member of r power n. So, what is x r power n? R power n is the set of ordered n tuples, where this x1, x2, xn all are real numbers. Then, if you are defining d1 of xy equals sum of modulus of xi minus yi, where the modulus running over 1 to n, then this one forms the metric on r power n. Therefore, r power n together with this metric is an other example of an metric space. So, this term more precisely written as x1 minus y1 plus modulus of x2 minus y2 etc. up to modulus of xn minus yn. So, this will forms the metric on r power n. And the second one, instead of d1, if one can replace, we are not changing the space, just we are changing the metrics. So, here D2 is defined as square root of modulus of xi minus yi power 2, where I running over n to n forms the metric on r power n. Here noted that n must be greater than 1, as if one can take n equal to 1, then check whether it will form the matrix, because if you are taking n as 1, we have only xi minus yi, then x1 minus y1, it is a modulus of x minus y of square root power 1 by 2, which is equal to modulus of xi x1 minus y1, which is called the usual matrix, which we discussed in real number system. Okay. The third matrix, so here before that, this metric whenever is n is greater than 1, because we already defined the metric in real number system. If you are taking n equal to 1, which is equal to real number, this matrix becomes the standard metric. If n equal to greater than 1, that means in r power n, then this one forms the other metric, and this is the maximum or supremum metric on r power n, which is defined as we need to find the distance between all the order pairs and taking the maximum. For example, this one is if we have taken two element x1, x2, xn and y1, y2 up to yn, then find the modulus between difference between x and y, x1 minus y1 and x2 minus y2 up to xn minus yn. Then take the maximum among all this pair, then it forms the metric on r power n. This metric we are denoting as d infinity or maximum metric in r power n. Okay. These three distance or matrix functions make r power n as a metric space. Now, instead of general n, if one can take n equal to 2, then the second metric is defined as modulus of x1 minus y1 plus modulus of x2 minus y2. Now, this function, this is not f, d is a function from x cross x, we are taking x as r power 2. So, x cross x to r is defined as like distance between x and y is defined as this term, then this will forms the metric space. This is a very particular case of when you are taking n equal to 2, then you will arrive this one, then x together with this d forms the metric space. That metric we can call it a Manhattan matrix. Instead of this one, if you are taking this metric is behaving like if you are taking n equal to 2, then this metric is defined as d2 of x comma y is defined as, we will write this one as modulus of x1 minus y1 power 2 plus x modulus of x2 minus y2 power 2 power 1 by 2. So, in r power 2 we have two matrix, this one d2 and this Manhattan matrix. Manhattan matrix may be the particular case of dn of x y is a particular case of when you are taking n equal to 2, then these two matrix d1 and d2 can be defined like this one. Then one can see what is the difference between this one by just finding the distance in the r power 2 plane. If you are taking two elements like here, this is, you can call it as x1 and y1, this you can call it as x2 and y2. Then this metric usually finding the distance between these 2 points. Whereas what is this point? So here our x1, here our y1 assume, and here our y2, and here our x2. So this matrix D1 matrix, it find the distance between x and y in this direction, and finding the x1 direction, this direction, this is y2 minus y1, this is x2 minus x1. So this metric find the distance between 2 points by vertical direction and the horizontal direction, whereas this one for finding the distance between 2 points diagonally. So this is the two metric on r power 2. Okay, fine. So these are all some examples of the metric space. When x equal to r power n, what can define different metrics. Now let me define what is the open ball and closed ball in the metric space. Let x comma d be a metric space. If a point x is belongs to x, and for any positive real number r greater than 0, the subset b of x comma r is defined as set of all y belongs to x such that distance between x and y less than r. So take any point x or any given point x in the metric space and a positive real number r. This set is defined as set of all the points in x such that the distance between this point and x must be less than r. So in the same way, take a point in x and a positive real number r greater than 0. Instead of distance between x and y less than r, if you take distance between x and y less than or equal to r, we are using this notation. Then the first one is called the open ball and second one is called the closed ball. So with respect to the space and the metric, the open ball and closed ball will vary. For instance, if you are taking any real number system r, so we are taking r with the usual metric d. The usual metric d is defined as modulus of x minus y in 2 point in the real number system. So we will see what happened in the closed ball and open ball. If you are taking any number x here, then if this is the given point x is here, then y, this set consisting of all the point with the number x minus y less than some given number r. So it means that this y belongs to in the interval here x minus r, x is here, so x minus r in the left and x plus r in the right. So it containing all the numbers between x minus r to x plus r, whereas this number x plus r and x minus r will not be the member of this set, whereas here in this set this containing all the point in between x minus r and x plus r, also it containing the two endpoints of this interval. So it is one can get the open interval by this definition and one can get the closed interval from this definition. Now see here r with the usual metric is given. If you are taking x naught equal to 2 with the radius r equal to 1, so our x naught is 2, x naught is 2, then what is the open ball and closed ball we need to check. So, here x naught is 1 at a given point, radius is 1. So, 2 minus 1 one can get as the interval 1 and 2 plus 1 one can get as the interval 3. So, one can get the ball of open ball of center x naught, here x naught is 2 and the radius 1, one can get the open interval 1 comma 3, whereas the ball of the center x naught and the radius 1, one can get the closed interval 1 comma 3. So, here open ball will give the result the open interval 1 comma 3 and the closed ball will give the interval 1 comma 3. So, as I mentioned previously, the open ball will vary based on the set as well as the metric. So, with respect to the usual metrics and the given point 2 in the real number system and radius 1, one can get the open ball as 1 comma 3 and closed ball 1 comma 3, whereas instead of usual metric, if one can change the other metrics, what is the open ball and closed ball, then you can see we already defined the number 0 and 1. So, in the 0 and 1, if you are taking x naught equal to 2 and radius equal to 1, then the ball of open ball of 2 comma 1 containing set of all x belongs to R such that the distance between 2 comma 1 must be less than 1. So, as per the discrete matrix, if the 2 points are equal, it will gives the result 0. If not equal, it will gives the result 1. So, this the distance we are taking R is less than 1. The only possibility is here it is 0. So, it will containing only the number 2 because the radius is 1. In the same way, the closed ball 2 comma 1 will contain the, here radius is 1, that means instead of 1 we can write set of all x belongs to R such that the distance between 2 comma 1 less than or equal to 1. So, if the radius is less than 1, the only possibility is 2. If radius is equal to 1, then it will cover all the points. So, which is equal to all real number system. In the similarly, if you are taking x naught equal to 5 and R equal to 1, the radius is same and just I am sending the center point, you will get the same. Similarly, you can get the same number singleton set and the closed ball as the whole real number. Whereas, in this case for open ball and closed ball, we are getting open interval 1 comma 3 as a open ball, closed interval 1 comma 3 as a closed ball. Whereas, here by changing only the radius, we are not changing the radius, we are just changing the metric, then the open ball is here and the closed ball it is changed as like this one R. So, with respect to the metric, the open ball and closed ball will change. So, here is the another example. So, usually whenever the radius is less than 1, one can get the singleton set. Whenever the radius is less than or equal to 1, then they will get the whole space. Then let me define some important points in the metric space. Let x comma d be a metric space and A is a subset of the metric space X. a point x belongs to A is said to be an interior point of A if there exists a real number, more precisely positive real number, such that the open ball of x comma r containing in A, then we can call this x as a interior point of A, because we already defined what is an open ball. Open ball is a distance between set of all y such that distance between x comma y must be less than r, it containing all the points. So, if this is a subset of A, then one can say the x is a interior point of the set A. That means you can take one point in the set and draw the open ball with respect to this point. If that open ball fully contained in the set, then we can call it as the point is an interior point. Otherwise, alternatively we can say if this set is contained in A, means if you are finding the intersection between these two sets, one can get the same set B of x comma r. The open ball intersection A can get the open ball same ball. So, here the x is called the interior point of the set A. Then what is the limit point? The next definition, a point x belongs to x is said to be a limit point of A if for every r greater than 0, the open ball intersection A must be non-empty. In other words, each open ball centered at x and radius r contains at least one point of A other than x. That means, then what is the difference between the interior point and the limit point? So, here x is a metric space and A is a subset of a metric space X. For defining the interior point, we are taking the point x belongs to A. X belongs to A. If you draw the open ball centered at x, if this open ball fully contained in A, then this x is called the interior point. Also, here while drawing the open ball, we are taking the there exists at least one r greater than 0. If this ball is contained in A, then we can call it as a x as a interior point. Whereas here we are taking a point x in the space, not in the set. X is belongs to x, and we are finding for every r greater than 0. If you are drawing any open ball, sometimes open ball can be called as the open neighborhood. If you are calling, if you are drawing the open ball with centered at x, if the open ball intersect the set A, then we can call it as x as a limit point of A. So, the difference between interior point and limit point is, here we are taking the point in the set, whereas here we are taking the point in the space, and for every open ball with centered R intersect the A, then it is called the limit point, whereas here there exists some radius, if this open ball is contained in A, then it is called the interior point of A. Now, let us discuss some example of the interior point and limit point. If let x equal to r with the usual metric and let A belongs to open interval 0, 1. If you are taking x is as 1 by 2, so our metric space is R with usual metric, R with the modulus, and the point x is 1 by 2. So, we are taking the open interval 0 comma 1. The point is 1 by 2 is here. So, x is 1 by 2. We need to check whether this 1 by 2 is the interior point of this set A. So, for finding the interior point, there exists a neighborhood. If you are choosing R as 1 by 4, then one can get the ball of 1 by 2 plus 1 by 4, one can get 3 by 4, and R is 1 by 4. So, 1 by 2 minus 1 by 4, one can get 1 by 4 here. This open ball fully contained in the space or the set 0 comma 1. Therefore, this 1 by 2 is a interior point of the set 0 comma 1. There exists at least one radius. If this ball fully contained in the set 0 comma 1, then this 1 by 2 we are calling as a interior point of the set 0 comma 1. Similarly, if you are taking x equal to 0 is a limit point of A, because so here 1 by 2 is an interior point of 0 comma 1 for the same set. For the same set 0 comma 1, I want to verify this is my set A and my space is R. Now, I am taking the element x equal to 0 in the space R, not in the set. So, I am taking x equal to 0, which is belongs to R, not belongs to A. Obviously, if you are taking any point here, it will intersect. That is, no, this is a trivial, but now I am taking the point other than the set A, x equal to 0. Then, if you are drawing every neighborhood with centered 0. So, this is my center. So, if you are drawing any neighborhood, any r greater than 0, 0 plus r will get here, 0 minus r one can get here, 0 minus r, this is 0 plus r. So, if you are drawing any open ball with centered at 0, obviously it will intersect this set. Therefore, this 0 is a limit point of A. Similarly, if you are drawing any neighborhood with centered 1, then 1 plus r is this side and 1 minus r is this side. Again, this center 1 and radius r, this ball will intersect the set 0 comma 1. Therefore, the number 1 is a interior limit point of the set this 0 comma 1, whereas this 0 and 1 is a interior point of A. The question is 0 and 1 is the limit point of 0 comma 1 and 1 by 2 is the interior point of 0 comma 1. Now, the question whether this 0 and 1 are limit point of the set 0 comma 1. Obviously, this is not an interior point of the set 0 comma 1, because if you are drawing any neighborhood with centered 0 with the positive radius, then you can get right side, this is 0 comma 1 and 0 plus r is this side and 0 minus r this one. Then this open ball, the right side it will contained in the set 0 comma 1, whereas minus r comma 0 is intersection the set 0 comma 1, one can get the empty set. That means, this set is not contained in 0 comma 1, therefore, 0 is not an interior point. Similarly, if you are drawing the any neighborhood who centered 1 with any radius, it will follow the same thing. That means, r comma 1 plus r intersection 0 comma 1, one can get the empty set. Therefore, this 1 is not an interior point of the set 0, 1. Fine. Let me define open set and closed set based on this interior point and limit point. Let X be a metric space and A is a subset of X. The set A is said to be a open in X if every point of A is an interior point of A. If you want to say the set A is an open ball, every point of A is an interior point of A, then we can call it as an open set. A is an open set. And similarly, a subset A of a metric space X is said to be a closed set. A contains all its limit points. A contains all its limit points. Then set A is called the closed set. And next definition, a set S in a metric space X and the closure of S is denoted as S bar is defined to be, that means S closure is defined as S union limit point of S. So, the closure of the set is defined as S union and its limit points. This is the definition of the closure. S is perfect. The set S is called perfect if it equal to the set of all its limit points. That means S equals set of all its limit points, then S is called the perfect set. The next definition, let X comma D be a metric space and let A belongs to X. A subset B in A is said to be a dense in A for every element X belongs to the set B, and for every epsilon greater than 0 the open ball intersects A, then we can call the set B is dense in A. So, you can take a metric space and take two sets A and B is a subset of A. One can say this B is dense in A. Every neighborhood of B intersect the set A, then we can call it as B is dense in A. Let me give some example of open set, closed set and dense set and perfect set. Let S you can take as 0, 1 in the metric space R. This forms the open set in R. So, what do you mean by the open set? If it contain all, if you are taking any point in X, if the X is an interior point, then the set is called the open set. For any element X belongs to 0, 1, there exists a positive number epsilon greater than 0 such that this X minus epsilon and X plus epsilon is fully contained in 0, 1. See, we are taking the interval 0, 1 for any number, say for example, any epsilon X we are taking inside this set. There exists a epsilon. We need to appropriately choose this epsilon. Suppose we are choosing epsilon in large enough, maybe it will goes like here to here, X minus epsilon, X plus epsilon. Whenever if you are reduce this epsilon up to this, then one can find the optimum epsilon, X minus epsilon, X plus epsilon is fully contained in the set 0, 1. So, one can find the optimum epsilon such that this open ball fully contained in 0, 1. So, every point of S is a interior point, therefore, this S is an open set. And What is the closure of the set 0, 1? So, closure is defined as the set S union of their limit points. So, what is the limit point of 0, 1? As we already discussed, 0 and 1 both are the limit point of the open interval 0, 1. If you are taking the union, we will get the closed interval 0, 1. So, the closure of a set 0, 1 is closed interval 0, 1. And for a closed set, the example of the closed set, if you are taking the closed interval 0, 1, then it contain all its limit points. First of all, what we need to identify, what is the limit point of 0, 1. So, if you are taking the interval 0, 1, so what do you mean by the limit point? For if you are taking any x here, if you are trying any open neighborhood centered at x, that must intersect this point. If the points are belongs to this open interval, there is no problem. Obviously, it will intersect this point other than this x. Only we need to check in the endpoints. If you are taking 0 here and make it as a center of the ball b of 0, r, you can choose any r, then it will contain at least one point, or it will intersect the set 0, closed interval 0, 1 is non-empty. Therefore, this 0 is a limit point as well as this 1 is the limit point. So, 0, 1 also the member of closed interval 0, 1. Therefore, it contains all its limit points. Therefore, closed interval 0, 1 is the example of a closed set. Whereas, if you are taking 0, 1, the same manner open interval 0, 1 does not include the end point 0 and 1. Therefore, this open interval 0, 1 is not a closed set. Then, the example of the perfect set, let S is a closed interval 0, 1, every point of S is a limit point. Every point of S is a limit point. So, S is a perfect set. So, we have the example of open set, closed set and perfect set. Before moving for the dense set, we will check whether the Cantor set is closed set or open set or perfect set, because as we already seen the how to construct the Cantor set, we need to know their properties. The Cantor set is closed and every point of Cantor set is a limit point, hence it is perfect. How this is true? So, if you want to check the Cantor set is closed set, we need to verify that it containing all its limits points. I am just recalling the construction process. We started with the interval 0, 1 and dividing 3 equal parts and removed this one and obtained this stage 1 by 3 and 2 by 3, 0 and 1. If you continue this process, the next one which will divide 3 equal parts and removing the mid one and 3 equal parts and remove the mid one can get these two sets and so on. So, now we need to verify whether this set is a closed set. That means, it containing all its limit points. Suppose if you are taking an element x belongs to C. So, C is the intersection of all the iterations. So, C is the intersection of C n, where n varies from 0 to infinity. This is C 0, C 1 and so on. If you are taking x belongs to C, then for every neighborhood, for every r greater than 0, find the open ball centered at x and radius r, then it will definitely intersect the set C, because x, if you are taking 1 by 3, it will come to here, and if you are taking x as 1 by 3, then you can take any r is greater than 0, then the ball of 1 by 3 and 0 intersection C is non-empty. It will contain many points, infinitely many points of C. Therefore, this 1 by 3 is the limit point. It is true for all the x when you are taking from the C. So, C is a closed set, that means the Cantor is a closed set. Moreover, if you are taking all the limit point, because C is contained in 0, 1. C is contained in the interval 0, 1. If you are taking any point in C, it is an limit point. If you are taking 0 and 1, if you are taking 0 and 1, it is also the member of C. Therefore, C containing all its limits point. So, C is a perfect set. That means the Cantor is a closed set, Cantor set is a perfect set. Now, let us see the example at a set which is not a perfect set. If you are taking S equal to 0 union open interval 1, 2, the point 0 is an isolated point. So, it will not containing all its limit point. Therefore, S is not a perfect set. Now, we will discuss some examples of the dense set. The real number system, take the irrational numbers. If you are taking any x in the irrational number, and for any r greater than 0, the open ball x with the r intersect the r. That means this is always non-empty. Therefore, the rational numbers is dense in R. Similarly, the irrational numbers also dense in R. You can take any number in the irrational numbers as well as x belongs to rational numbers, then the ball x with r for any r greater than 0, then this one with the r is non-empty. Therefore, this both the set rational and irrational number both are dense in R. Now, an open interval 0, 1 is dense in the closed interval 0, 1. A open interval 0, 1 is dense in the closed interval 0, 1. So, you can take any point here and draw the neighborhood, it will intersect the set 0, 1. Therefore, 0, 1 is dense in closed interval 0, 1. So, if you want to say B is dense in A, you can find the closure of B which is equal to A, then one can say the B is dense in A. So, closure of open interval 0, 1 is closed interval 0, 1. Therefore, it is easy to verify that this interval is dense in closed interval 0, 1. So, finite set is not dense in R, since if you are taking this name, finding the closure of this one, it is not equal to R. Therefore, the set is not dense in R. So, obviously, any integers, if you are taking any integer, its limit points are only the numbers which it contains, that means it has the empty integer, it is not dense in R. All the polynomials are dense in this space, the set of all continuous functions on 0, 1, which we will discuss later. The set of all polynomial is dense in continuous functions, the space of continuous function in 0, 1. So, let me give the some result related to the open set and closed set. In a metric space X, empty set and the space is always an open as well as closed. Therefore, these two sets are called the clopen sets. An arbitrary union of open set is open. A finite intersection of open set is an open. An arbitrary intersection of closed set is a closed set. A finite union of closed set is a closed set. Every neighborhood is an open set. So, neighborhood in the means we are considering the open ball as I mentioned. So, open set is also we can call it as a neighborhood. Okay, fine. Here the note that the finite intersection of open set is open, whereas finite union of closed set is closed. Similarly, arbitrary union of open set is open, arbitrary intersection of closed set is closed. By using this result, one can prove that the Cantor set is intersection of arbitrary collection of the closed interval. Therefore, we can say Cantor set is a closed set. So, Cantor set is the arbitrary intersection of closed sets. Therefore, we can conclude that C is a closed set. Then, let me define what is the compact set. Let X be a metric space and E be a subset on the metric space. By an open cover of the set E, we mean a collection of open subsets of X such that E contained in the union of this collection. Then we can say this collections forms the open cover for the E. You can take any subset in the metric space X, a collection of open subsets of X in the metric space. If E is contained in this union, then we can call it as E has an open cover. Let X be a metric space and K be a subset of X. Then the set K is called the compact set if every open cover of K contains a finite subcover. Then we can call it as this set as a compact set. A set K is said to be a compact set if every open cover of K contains a finite subcover. That is, if this is the arbitrary open cover of K, then there are finite number of indices alpha 1, alpha 2 up to alpha n such that union I varies from 1 to n, G of alpha I contains the set K, then we can call it as K is a compact set. The example of the compact set is the closed interval 0, 1 is the compact set. Closed interval 0, 1 is the compact set. If you are finding any open cover, we can give at least one subcover. Therefore, we can call this closed interval 0, 1 is an example of an compact set. Say for example, for covering this one, one can take this set minus 1 by n, 1 plus 1 by n. So, this is my Zn, V of alpha n. When you are taking n as 1, 2, 3, it will varies that this one minus 1, n, 1 plus 1 by n. This is an open set. If you are taking the union of all the set, then 0, 1 contained in this set n equal to 1 to infinity minus 1 by n, 1 plus 1 by n. So, this set is contained in this one, therefore, this is a open cover for 0 comma 1, whereas if you are taking n as 1, then we will get minus 1 comma 1. Instead of n equal to 1, if you are taking n equal to 2, one can get minus 1 by 2 comma 1 plus 1 by 2 will get 3 by 2. So, 1.5, obviously this contains the 0 comma 1. So, this singleton element is enough to contain the set. So, this open cover has at least one finite subcover, therefore, this set is a compact set. Whereas, if you are taking the open interval 0 comma 1, whether it is a compact set, we need to verify. But if you are taking this interval open cover 1 by n plus 1 plus 1 by n, this, if you are taking the union n is 1 to infinity, this contain the set 0 comma 1, but we cannot find the finite subcover which contain the set 0 comma 1. Therefore, the open interval 0 comma 1 is not a compact set. The next, then the singleton set X in any metric space is a compact. Any finite subset of X is an compact. A closed ball in R power n is compact. The open interval is not a compact. The set R is also a not compact. If you are taking the real number 0, here minus infinity, here plus infinity. So, for cover this one, we can take this open interval. This open interval, if n equal to 1 to infinity, if you are taking any real number x belongs to R, it belongs to this interval. It belongs to this interval. So, R is contained in this open cover, but one cannot find the finite subcover that for this open cover which covers the number R, set R. Therefore, R is not a compact set. So, let me stop here. Thank you.